Bien, mesdames et messieurs, je suis très heureux de vous accueillir ici ce soir. Il reste encore à peu près une dizaine de places dans les premiers rangs. Si certains veulent s'avancer, ça permettra à d'autres de s'avancer depuis le fond. N'hésitez pas à venir encore dans les premiers rangs. Mesdames et messieurs, je suis extrêmement heureux, en tant que recteur de l'Université de Genève, de vous accueillir ici ce soir. Je crois que le public qui est présent ici démontre à l'évidence que nous savions depuis longtemps, c'est l'intérêt que représente la science, les sciences fondamentales, les sciences appliquées pour la population genevoise, pour l'université et beaucoup plus largement pour la population. Je crois que ceci représente véritablement un point d'une très grande importance pour nous tous. Ça me permet de remercier ici la Fondation Wright et bien entendu je salue ici Madame Wright, je salue le président de la Fondation, Maître Jean Patry, de tout ce qu'ils font, de tout ce que la Fondation Wright fait pour l'université, pour la population. Ce partenariat, je crois que c'est la 14e fois qu'est organisé le Colloque Wright et sont organisés ici Colloque Wright et je crois que ceci démontre comment donc, depuis bientôt 30 ans se poursuit, s'est construit et se poursuit une tradition absolument d'exception. Comme vous le savez, les semaines des Colloque Wright sont des semaines tout à fait particulières où il peut se générer une magie dans l'échange entre les scientifiques qui sont présents et le public. Et je suis convaincu que cette semaine sera à la hauteur des plus exceptionnels Colloque Wright que nous avons eus au cours de ces dernières années. Donc je suis extrêmement heureux de vous accueillir et je passe la parole à Maître Jean Patry, président de la Fondation, qui va vous en dire plus.
Bonsoir, la Fondation Wright est vraiment très heureuse de vous accueillir ce soir et de vous voir aussi nombreux. J'y reviendrai, le sujet que nous avons choisi à première vue nous paraissait un sujet ardu, mais votre présence nous réconforte et c'est déjà la récompense des efforts qu'ont fournis tous les organisateurs de ce colloque pour que ce soit un succès. Il y a à peu près 30 ans, Dudley Wright, qui était un entrepreneur des États-Unis d'Amérique qui s'était installé au bord du Léman, a estimé qu'il était nécessaire, pas seulement à l'échelon genevois, à l'échelon planétaire, de rapprocher le grand public avec les travaux scientifiques de pointe et que c'était une nécessité impérative pour la société en général. Il a créé ce qui est devenu le Colloque Wright pour la science. Il a souhaité que cela s'intègre dans le cadre de l'Université de Genève, qui était sa ville d'adoption, et c'est ce qui explique notre présence tous les 2 ans à Genève avec un colloque. Je voudrais saluer ici une forte présence de la famille de Dudley Wright, son épouse, plusieurs de ses enfants, des petits-enfants, qui assurent la tradition de la famille Wright axée sur le développement scientifique de l'humanité. Il a voulu que ça s'intègre dans l'université et l'université a accueilli ces colloques Wright avec énormément d'enthousiasme. Elle se donne un mal fou pour nous aider à les organiser et je voudrais la remercier ce soir de son ouverture, de son aide, de son appui qui est un encouragement pour les membres du conseil de fondation et les membres du comité scientifique pour continuer cette œuvre et la développer davantage. Je voudrais citer en particulier le professeur Giamarchi qui s'est chargé de l'organisation scientifique du colloque. Je voudrais citer le docteur Rabou qui est le chef du service de presse, mais bien plus dans l'université, qui est un enthousiasme de la Fondation Wright et qui nous appuie dans toutes nos initiatives, je dirais. Je voudrais citer l'organisme Passerelle Science Cité, que la Fondation Wright a encouragé dès sa création et qui participe considérablement à l'organisation de ces colloques. Et enfin, je voudrais citer l'organisatrice logistique du colloque. J'aime mieux vous dire que ce n'est pas une mince affaire, Madame Lozano, qui se trouve quelque part et grâce à qui tout fonctionne bien au niveau de la logistique. Le sujet, la révolution quantique, n'est pas un sujet tout simple. Mais il m'a fait réfléchir un tout petit peu à ce qu'était la science. Eh bien, j'arrive à la conclusion que si, au XVe, XVIe, XVIIe siècle, nous avions de grands explorateurs comme Christophe Colomb, Vasco da Gama, qui exploraient notre Terre et qui l'ont découverte. Aujourd'hui, les explorateurs, ce sont les scientifiques. C'est eux qui font les découvertes. Sur la Terre, il n'y a plus grand-chose à découvrir en elle-même, mais ils font des découvertes quant à la fonction de notre système, à la façon dont nous fonctionnons et dont le système planétaire fonctionne autour de nous. Et ces découvertes peuvent être des révolutions en elles-mêmes. On entendra la révolution quantique, mais il n'y a aucun doute que ces découvertes apportent à notre société des révolutions. Les découvertes des grands explorateurs des siècles passés ont apporté des modifications considérables dans notre monde et dans notre société, mais les découvertes scientifiques qui se font aujourd'hui, en particulier dans le domaine quantique, ont apporté des révolutions probablement plus profondes et plus durables ou plus manifestes que ce que l'on connaît sous le nom de la révolution industrielle. Et j'aimerais simplement citer, sans m'étendre, sur la révolution des communications, télécommunications, qui est largement due à cette science quantique, révolution qui assure ce que l'on appelle aujourd'hui la mondialisation. Je pense qu'il n'est pas juste d'attribuer la mondialisation à l'Organisation mondiale du commerce, qui a son siège à Genève. Elle ne fait que suivre. Cette mondialisation est le résultat direct d'une communication instantanée à l'échelle planétaire. Et cette mondialisation ou cette communication a aussi une influence sociale, naturellement, mais une grande influence politique. La censure n'étant quasiment plus possible ou efficacement possible avec les moyens de communication. Je vous souhaite un très bon colloque. Avant de donner la parole au professeur Fischer qui introduira le conférencier de ce soir, j'aimerais vous dire que nous avons été débordés par votre enthousiasme. Pardon à ceux qui doivent suivre cette soirée assis sur les marches ou éventuellement debout, mais ça vous rappellera vos années d'étudiants. Demain, nous serons organisés et il y aura une autre salle dans laquelle vous pourrez suivre la conférence par vidéoconférence. Merci beaucoup et bonne soirée. Professeur Fischer, c'est à vous.
Ladies and gentlemen, it's my pleasure to introduce the first speaker of this year's Wright Colloquium. I will do this in English. I hope that the translation works. Is that working? Okay, fine. Professor Mannert started his scientific career in the University of Tübingen in Germany by publishing his first scientific work in 1986. This happened to be the same year that another discovery was made in another place, namely in Rüschlikon, close to Zurich, a discovery that came to influence strongly Joachim Mannert's career. And that was the discovery of the high-temperature superconductors by Alex Müller and George Bednold, which came to revolutionize the field of superconductivity. Now, although he was initially involved in other very interesting things. I remember we met and discussed the things he did at that time in his early career, and he decided to quickly switch to the new field of high-temperature superconductors. And he did so by going to the IBM laboratory at Yorkton Heights in the US, where he worked with some of the most eminent people in the field, and he had the idea to do a simple but very important experiment. What he did was that he took a grain of that material here, and then he took another grain of that material here, and he put them in contact, and he sent the current through. And then he studied how that passage of the current changed when you turn one of these grains. It sounds simple and not very profound, but in fact it turns out that the answer to that question depends on the very basic quantum properties of the superconductor that he studied. And moreover, this is a central question for the application of the superconductor. So it came that the work of Jochen Mannhardt became the scientific sort of basis for the technology that has been developed since in producing wires and tapes for practical application that he certainly will mention to us in his talk. Following up, he came back to Europe, and then he went to Zurich, to the same laboratory where this discovery was made, and he worked there for 7 years, and then he went to Germany, back again to Germany, to the University of Augsburg, where he is appointed professor, and where he is, as of today, still a professor there. He is also the spokesman of a large collaborative German project on the research of complex materials. Following up on his work on the high-temperature superconductors, Professor Mannhardt has also become one of the leaders worldwide of what is known as oxide electronics. In fact, this was a field that developed in the wake of the development or discovery of the high-temperature superconductors. And here I am particularly proud that there has been a close collaboration over the years with Professor Mannhardt and our NCCR in Geneva, Mannhardt. And I would like in particular to mention the very successful collaboration he has had with Professor Jean-Marc Triscone over the recent years. Professor Mannhardt has published well over 200 scientific articles. He has received a number of distinctions and prizes. I would like to mention especially the prestigious Leibniz Prize that he received in 2008. Superconductivity, which is the topic of today, spans from very profound and sophisticated theory to large-scale practical applications in motors and generators and things like that. To present this very broad and complex field to a broad audience in an understandable manner is nearly impossible task. Knowing the high qualities of Professor Mannhardt in this matter, we are extremely grateful that he accepted this difficult challenge. Jochen, the floor is yours.
Yeah. Dear Mr. Patry, President of the Dudley Wright Foundation, dear Professor Wasserli, Rector of the University of Geneva, dear Oyston, Director of MANEP, and dear Professor Giamarchi, dear Thierry, I've been told you are conductor and supervisor of this colloquium, dear attendants and colleagues, dear friends of science, welcome to this evening and to my presentation today. In this talk, I'd like to present to you the amazing, beautiful, and bizarre laws that determine how nature, the world around us, and also we work, how we operate. And this topic is very close to my heart. It is fascinating and truly important. Therefore, I'm very grateful that the Dudley Wright Foundation and also the University of Geneva have devoted this year's colloquium to this fascinating topic. And I'm very glad that I'm giving the opportunity tonight to share some of this fascination with you. Now, the first foil I have here, the first view graph, shows, maybe I can dim it down a little bit, shows how we usually think the mechanics of our world works. So you see this clock here, and there are, of course, wheels, and there are levers, there's rotation, there are forces. And if we add to this behavior electricity, thermal effects, and optics, we may think we can describe the whole world, even the functioning of our bodies. You know, the bones are just levers that rotate around the joints. The muscles convert chemical energy into rotation. The heart is a pump that pumps the blood through the system, you name it. This understanding of nature, that's the understanding one had until the beginning of the 20th century, is called classical physics. But is this really our world? Is there a reality below this physics, below our world, with laws that are different from the laws which we know, that we need to understand? Indeed, we live in a different world, and we live in a world that is controlled by very strange and bizarre laws. And these laws I'd like to present to you, at least some of them. And these laws and this behavior of nature is not a speculation. That's a scientific fact. And that becomes obvious already if you just look at these pictures here. The forces that stabilize the wings of the butterflies, these fragile wings, are forces that cannot be described by classical physics. And the delightful smell of the colors of the flowers and the beautiful colors, the color of the green color of the chlorophyll and the functioning of the chlorophyll extends far beyond the reach of classical physics. Indeed, we see already that classical physics fails to describe nature if we look at dead matter in detail. So if one looks at the clock which I showed to you, or here for this example, on a silicon wafer with high magnification using a microscope, one sees that the matter is built out of the atoms. You see here the silicon atoms. And if we zoom in greater detail, for example, in this atom, as we have done here in Augsburg, these are images of my group, we see here one silicon atom, and we see the structure inside the atom. Let me mention here that the magnification of this image is really tremendous. If we take an atom and enlarge it to this size, we have a big magnification factor. If we take the same factor and apply it to this image, if we would magnify it again with the same factor, we would be at the orbit of the moon, in fact. Now, classical physics fails to describe the atoms. Indeed, the existence of the atoms, as they are, they contradict classical physics. Why is this? Well, what we see here are the electrons basically circling around the nucleus, as it would be described in classical physics. Classical physics would say, okay, the atoms, we cannot explain why they exist, but the atoms one can describe like a little solar system. There's the nucleus at the center, that's the sun, and this electron, a little indivisible particle, circles around it. But this, in fact, cannot exist. Classical physics would say this is unstable because the electron, which is charged, would instantaneously lose energy and just crash into the nucleus. So classical physics says these atoms are unstable. Our world would be unstable. what is happening, in fact, is that the electrons don't act as particles, but these electrons, as we understand them today, behave as waves. In fact, these waves are the orbitals that you know from school, from the chemistry or from the physics courses. And science says today that, in fact, every piece of matter, so electrons, neutrons, apples, golf balls, are waves or are built out of waves. You may have heard about it, and it may sound strange. You may have gotten maybe a little bit used to it. So I'd like to discuss this in a little bit more detail, just by mentioning or by describing how classical physics would describe a particle and a wave, because in classical physics, particles and waves are completely different. An example for a particle, a nice example, is of course a stone, as you can see it here. So a stone has of course a certain shape, has a certain color, has a surface texture, and of course the stone has the property that if there's one stone, there cannot be a second stone. So if you take a second stone and try to place it on the position where the first stone is, both repel, both are very hard, you cannot do it. You can take a stone, you can spin it, you can throw it, you know what a stone is. A wave is something completely different. A wave is an excitation of a medium, like for example in this case, a water wave, where the water is excited. What is a wave? You can imagine a wave starts by a water particle or droplet moving up and down and exciting its neighbor also to move up and down with a little bit of a delay. And like the wave of fans in a stadium, this wave then is propagating through the matter. And a wave can spread out over large areas, and in contrast to a particle, where there is a wave, there can be a second wave. Waves can penetrate each other, and something funny happens there, which you know, but I'll just repeat the obvious. If two waves overlap, it is very important how they overlap. If the peaks of the two waves overlap and the troughs of the two waves overlap, one obtains a wave with big peaks and with deep troughs. If the waves overlap, however, that a trough meets a peak and a peak meets a trough, the two waves cancel and both are gone. So, if we say that, and if we know every piece of matter is a wave, there are of course two obvious questions. First of all, how do we know that this is the case? And second, what does it actually mean? Because it seems so counterintuitive. Well, we know that this is the case because we can calculate with very high accuracy the behavior of these waves. And this is done by using an equation which I'd like to show to you. I'm reluctant to show to you equations. It's the only one which I'm going to show to you. And I do this also because the equation is, many physicists think so, the most beautiful equation in the whole of science. You may need to be a physicist to appreciate the beauty of this equation, but here it is. This is an equation which was conceived by a real genius, Paul Dirac, a British physicist, in 1928, and it describes the behavior of these waves which describe the particles. And the waves are given by this symbol psi here. That's the wave. The m is the mass of the particle that is described by the wave. And this term here, this factor, describes all the dynamics, all the peculiarities of the problem. This equation is amazingly accurate. It has made predictions which have been verified by experiments with an accuracy of 11 digits behind the comma. Imagine that's the most precise predictions, the most precise equation we have in the whole of science. Just to make it clear, 11 digits behind the comma, that is as if you had a bathroom scale for weighing in your bathroom, which has an accuracy of a millionth of a gram. And if you would have a theory, a model, to calculate your weight, you know, depending on what you ate yesterday and what you did, how many sports you did, and so on, to calculate your weight with an accuracy of a millionth of a gram, and you stand on the scale and both agree. If this is the case, you would think, okay, the model, the theory I have, really holds some truth, and this is the case for this equation. In fact, it never failed us. And this equation is also very powerful. It made predictions which Paul Dirac couldn't think about and hadn't thought about before he conceived this equation. And one of the predictions is the existence of antimatter. That's what this equation tells. What is antimatter? My students said I should explain what antimatter is in a sentence, and I'm trying to do it now. Antimatter is the following. If you have a stone and you throw it away, you have nothing. And if you would like to sound fancy like a theoretical physicist, you would say you're left with vacuum, nothing. Now, Dirac's equation says if you have a vacuum, you can take a stone out of the vacuum and throw it away, and what you're left with is an antistone. And an antistone is like a real stone. It has texture, it has color, it has shape. The only property that differs between a real stone and an antistone is that an antistone is built out of antimatter. And that was predicted based on this equation, and 4 years later, antimatter was indeed found in the experiments. It was Carl Anderson who discovered it in the cosmic rays. He didn't find, luckily, antistones coming down, but he found the antiparticles of electrons, positrons. And by now, one can even build anti-atoms and probably even anti-molecules. So this equation, Dirac's equation, is the cornerstone of a different physics that extends beyond the classical physics. And this is quantum physics. And the revolution that happened in these years, not only due to Dirac, but also due to others like Max Planck or Einstein, Schrödinger, Heisenberg, Pauli, that's the quantum revolution, which is the topic of this Wright colloquium. This equation also described or gave the first explanation why actually molecules hold together. It described the binding forces in the molecules. So without the physics behind this equation, without this quantum physics, there would be no molecules. And we definitely would not be sitting here in this audience in this nice evening, but we would be probably some clouds of gas drifting through the universe and maybe shimmering bluishly or whatever. In fact, this equation, because it predicts the existence of them, it describes the forces in the molecules so well, is solved every day thousands of times by the industry, by the chemical industry, by the pharmaceutical industry, to calculate the properties of molecules, to find out whether molecules can act as medicine or not. So they don't have to synthesize them, they just can describe them theoretically and calculate their properties. This is Paul Dirac, the man behind the equation. And he was British, as I said, but it's interesting, I'd like to mention to you that his father actually was Swiss. He was born up the river in Saint-Maurice, and his father then went to the UK and married in Cornwall the daughter of a British sailor. So that's the story behind Paul Dirac. Now, what does the wave actually mean? What does the psi mean? The psi says the following. the psi gives the probability to find a particle at a certain position in space. Actually, it's not the psi itself, it's sort of squared in a funny way, but that doesn't matter for us so much tonight. But what is important is that this probability is a really bizarre and curious probability. It's not the probability you would think about and the probability to which you are used. Let me make it clear with the following example. If you want to leave home and you're looking for your car keys, you may think, okay, the car key is either in, say, the bathroom or in the kitchen. If you don't know where it is, it's with 50% probability in the bathroom and with 50% probability in the kitchen. You find it in the kitchen, but you know, of course, that the car key was always in the kitchen. You just didn't know where it was. That's the classical view to which we are used. Here it's different. Here, in quantum physics, it's the following way. The wave of the car key is 50% of this wave is in the kitchen, and simultaneously 50% of the wave is in the bathroom. And it's only in the moment where you see the car key in the kitchen that the wave decides to be 100% in the kitchen, and at the very same instant, the 50% of the wave in the bathroom disappears. It collapses. And to me, it's frequently, mostly, the other way around. I look in the kitchen, there's 50% of the wave, but then the wave decides, hey, I'll be in the bathroom, and it collapses in the kitchen. So this is really a funny type of probability. And here you get already a first feeling that quantum physics is really completely different from our classical understanding, because the action on one place, finding the wave in the kitchen, causes a change of the wave somewhere else in space. So quantum physics is completely unlocal. It's not a local theory. An event at one space influences an event at the very same instant at a different position in space. And these are effects which have been found and studied, for example, by Professor Asbeck. And we'll hear a presentation of him on Thursday. And I'd also like to mention that great experiments and demonstrations of this behavior have been done by Professor Chizan here in Geneva. Geneva is one of the leading centers in the world on this area. Now, I'd like to go on and show you with two examples how strange and bizarre the quantum world indeed is. The first example is the following. Imagine you have a ball, so a golf ball or a soccer ball, and you play this ball, you roll it against a hill or a wall, as shown here. What happens in our daily life in classical physics? What are you used to? Well, it's very easy. The ball, because you kick it, rolls against the wall, and because where there's a wall, there cannot be a ball. The ball rolls up the wall, as shown here. It gets slower, loses its speed, stops, turns around, and leaves the scenery to the other side. That's what we are used to. Now, what happens according to quantum physics? What happens in the quantum world? Well, the ball, of course, approaches the wall. But we know, of course, we shouldn't think about say, an electron as a ball, but as a wave. We need to think about it as a wave. And the behavior of the wave, we understand, is described nicely by Dirac's equation. So we just have to find somebody who solves Dirac's equation for us and tells us what is happening. That has been done. So the wave approaches the wall, and then Dirac's equation says that in contrast to classical physics, although the electron or the ball is not allowed to be in the wall, it nevertheless leaks in a little bit. The wave enters the wall and decays rapidly in the wall, but there's a finite wave in the wall, which means that there is a finite probability to find the particle where it's not allowed to be. Okay? It starts to get funny if this wall is thin, because then the particle can leak out, of course, on the other side. The wave just continues on the other side. And what are we having now? Well, we have a big wave on this side. That's the allowed side. So we have a high probability to find the particle on the left side. But there's also some wave on the right side. So there is a finite probability to find the particle on the right-hand side. And this means that this particle has traversed here this wall, which is not allowed to traverse, but it nevertheless does it. And that has been confirmed experimentally millions and millions of times. And this is just property of matter. It happens easily for electrons, but it may also happen for larger particles, and it may even, at least according to quantum physics, may happen to you. So, if there's a wall, I'm not making this up. If there's a wall, you have a finite probability, if you walk against it, that you can actually pass through. I hasten to add that the probability is very, very small, so you need to repeat it frequently. And in fact, because the probability gets smaller with your mass, so if your mass gets larger, the probability gets down, and if the wall becomes thicker, it also goes down, that for yourself, that you get a decent probability to go through the wall, you need to try it much longer than the age of the universe. But nevertheless, there's a finite probability that you can actually go through it. This effect is called tunnel effect. Here comes another example, which I think is even more bizarre. Imagine you make out of a metal a small ring. So a small ring out of gold, for example. And small, I mean really small, so that the size of the ring is about 1/1000th of a millimeter. That sounds fancy, but it's in fact not. Everybody of you could do it just with standard equipment of the semiconductor industry to fabricate small circuits. Now, here I've drawn such a gold ring, and with a hole. And I'd like to discuss with you what is happening if we send an electron from one side of this ring to the other side. So this ball is an electron, and this arrow gives the speed, shows the direction in which the electron moves. Now, again, this is a quantum problem, of course, so we have to think about the waves. And therefore, we have symbolized here the wave of the electron by giving this surface of the gold this wave-like character, as you see here. Now, what is happening as the electron approaches the fork of the ring? Well, obviously, that's also what Dirac's equation says. There's a wave going on this side of the ring, and there's a wave going on this side of the ring. Both waves meet again, and because the lengths here are the same, we made a nice ring. They meet in a way that the peaks of the wave meets and the trough of the wave meets. So we get the same wave on the right-hand side as we have on the left-hand side, which just means that the electron here has the same probability as it has here and leaves the ring to the right-hand side. Fine. But look what is happening in between. Here we have a small wave, say 50% of the wave here and 50% of the wave here. That means that the electron, half of it, but it's an indivisible particle, you cannot split it, but half of the electron moves on this side and half of the electron moves on this side. And this has also been confirmed experimentally. And that was done the following way. One can add a little coil into the hole of this ring. And if one sends a current through such a coil, you know it from school, the coil makes a little magnetic field. And by adjusting the current, one can adjust the strength of the magnetic field. Okay, let's do it. This magnetic field in the hole shifts the waves a little bit with respect to each other. And one can adjust the current, we can really be tricky, in a way that on the right-hand side of the ring, a trough of the wave meets a peak of the other wave. And that means that both waves here destroy each other, and on this side there's no wave, which implies that there is no electron to be found here. So the electron cannot leave at this end of the ring, but it has to turn around and leave back outside the ring. So this means that by turning on this little magnetic field, we change the resistance of this ring. It cannot transport electrical current anymore. So this is a measurable effect, and that has been measured. And this effect only works, of course, if the electron actually goes on both sides of the ring, because if it was just on one side, these waves could not interfere. So this experiment proves that the electron actually exists on both sides of the ring, although it's an indivisible particle. You may say, how can it be? I'd like to have a look. And if you do an experiment to see where the electron is, if you look with a microscope, for example, the very instant where you see an electron, it's there where it is, and the wave on the other side disappears, and the ring becomes a conductor again. So this experiment has been done, and it was done in 1961 at the first time at the University of Tübingen, actually, by Professor Jönsson there. And the readers of Physics World, that's the journal of the Society of the British Physicists, they made in 2002, they elected the most beautiful experiment in science ever done. So they voted about experiments done by Newton and by the Greeks and by Rutherford and so on. And they elected this experiment as the most beautiful experiment in physics ever done. The situation here is even more astounding than you may think right now, because the electron here is influenced by the presence of the magnetic field in the middle of the hole. Now, you're used to the fact that magnetic fields or electromagnetic fields influence something else. For example, your radio in your kitchen at home is, of course, influenced by the radio waves emitted by the radio station. What is going on there? The radio station beams out the radio waves, and the radio waves travel from the radio station to your kitchen, and your radio uses its antenna to fish out the radio waves in your kitchen from the sky, and that's the signal, and the music comes out of your radio. Here it's something else. Here the magnetic field inside the loop here, influences the behavior of the electrons because it stops the current flow across the ring. But there is no magnetic field at the position of the electrons. So one can even shield the coil perfectly from the electrons. But the transport of the electrons, the flow of the electrons, is nevertheless stopped. So the electron here knows that there is a magnetic field inside, although the magnetic field is far away from the electron. This experiment has been done too, and also the control experiment has been done, that there is no magnetic field in the coil, which is perfectly shielded, and the electron can pass on. So again, this is an expression of the non-locality of nature. The electrons here, sense what is going on at a different position in space. Now, at this point, I've shown to you a number of astounding effects. I'd like to give you a little break in the following way. A postdoc, a scientist in my group, has solved the Dirac equation for such small rings as I just showed to you. And he calculated how the waves behave in these rings. And we found that the patterns which these rings show are really very beautiful. He put in, just for fun, nice colors. So he color-coded them well. And I like these images so much that I'm just going to show a few of them to you, just as a little break for you also to show you how beautiful quantum physics is. So these are the waves, these waves of these rings. That's how nature organizes itself. And this researcher actually is Florian Loder, and he's Swiss. We are very happy that we have him in Augsburg. Now, where are we in the talk? In the talk, I'd like to convey 3 messages for you to take home. 3 messages which I would be very happy if you would remember those after you leave. And the first message is the quantum world is beautiful and bizarre, and I hope that I've been able to make this point. But I can imagine that many of you now think, okay, crazy quantum world, but this is a completely different world, happening mostly with small elementary particles. That's not me, that's something else. I can safely ignore it. Which brings me to the second point. I think this is not correct. I'd like to show to you how useful quantum physics is for your daily life. And you may be wondering now, how does quantum physics affect myself? And I've an example for you here. And the example is the trouser of your pocket or a purse which you may have. Because I bet that maybe 90% of you have a cell phone with you right now. And a cell phone is nothing else than quantum physics cast into a little box. Let me illustrate this to you. We are using quantum physics daily. So this is just an X-ray image of a cell phone. And of course, as in a cell phone, there are all these microprocessors, these chips. Here's an image, which consist of millions of transistors. And every one of these transistors amplifies or switches signals based on quantum effects. Without quantum physics, a transistor could not operate. A chip could not operate. There would be no computers, there would be no cell phones, there would be no transistors without quantum physics. Without quantum physics, it would not have been possible to have the idea of a transistor. If there are lights on your cell phone, these lights are operated usually by LEDs, by light-emitting diodes. And these light-emitting diodes, they are pure quantum physics. They work the following way. There are electrons flowing in these diodes, and these electrons, they pass through areas with forbidden energies. And in transversing these forbidden energies, they emit quantum particles, quanta of lights, photons, and that's the light that you see. And that's not only important for your cell phone, but because this is a quantum process, it's very energy efficient. And in the next 10 or 20 years, these LEDs will change the lighting, which we're using in daily life completely, into a more efficient, far more efficient way of lighting. So it will save tons of energy and keep the planet at least a little bit cooler. Your cell phone may have 1 or nowadays even 2 CCD cameras. You remember the times 30 years ago, 40 years ago, when cameras in TV stage studios were big things. Now they are integrated into your camera. And this is because the chips have been invented, CCD chips, which work as cameras and are very, very small and, again, very efficient. These chips are, again, the CCD effect is a pure quantum physical effect. It's almost reverse the way the LEDs work. And actually, for this effect, 2 physicists George Smith and Howard Boyle, I think Howard Boyle, received the Nobel Prize for it last year in 2009 for the invention of the CCD chip. And if you use your cell phone to surf on the web, you're using, of course, optical fibers, which are not in your cell phone, but which connect, for example, the surfer which you use to surf with other surfers. So these optical fibers transport the signals. And again, how the light is created to pass on in the fibers and how it's detected again, that's also the optimization of the fiber, that's pure quantum physics. So you're using quantum physics really on a daily basis, very, very frequently, maybe more frequently than you're using a screwdriver or a pen. You just don't notice it because the companies that sell you these objects of quantum physics, they don't want to frighten you, so they hide all this physics behind nice user interfaces so that you don't notice. But in fact, I should mention here that, of course, a screwdriver and a pen essentially is also quantum objects because you wouldn't have them without quantum physics. Now, if you think about it, you realize that there's hardly any product in our economy that is not based on quantum physics. Our world economy completely rests on quantum physics, rests on phenomena which were not known 100 years ago and which started 100 years ago as very arcane, esoteric science done by people like Dirac or Einstein or Heisenberg. But now this is really the basis of all our industries. And this will continue in future. And there will be great progress, I'm absolutely sure, coming out and applications coming out of work that today is just work in the lab, that is research work in the lab. And I've listed here 3 topics. Quantum cryptography is an example. As I said, the group in Geneva of Professor Gisson is one of the pioneers there. It allows to send messages from one place to the other in a way that they cannot be eavesdropped on. Perfectly secure message transmission. Teleportation, you know it from Star Trek. Beam me up, Scotty. That has been done now with elementary particles. It may be impossible to do it with living people. I think the difficulties will just be too enormous. But with particles, it has been already done. Qubits, a very fascinating topic. The idea is to replace the bits, which are the basis of our computers, by quantum bits, which at the very same time can carry different states of information. And the hope is to build computers out of them, which are far more powerful than the best computers that we have today. And on Friday, we'll have a talk of Professor Blatt on this topic. But I'm sure, or I'm very positive, that the most important applications in future of quantum physics actually will come out of areas and ideas which we are not aware of today. So some bright student or scientist, maybe tomorrow, will have a fantastic idea how to use quantum physics, which will shape our future in the next decades. Now, at this point, I'd like to go ahead and show you a little bit about my own work, superconductivity, which again is a quantum physics phenomena, as Professor Fischer has introduced to you. What is superconductivity? Let me explain to you how current, how electricity flows through a conductor. If you have a wire out of copper or out of aluminum, and you look at it, so this is a picture, of course, a simulation. You'd see that there are the atoms and there are the electrons making the waves, the clouds, the orbitals around these atoms, as you can see here. But in a metal like copper or aluminum, there are also electrons which are in between the atoms and which are free to move. If one sends a current through a material, these electrons move and transport the electricity. That's how electric current flows. Now, this is not a lossless process because the electrons, as they flow, they bump into atoms here which may sit at wrong positions, or atoms which just vibrate too much because they are too hot, or they may bump into impurities. And by bumping into this atoms, energy is lost. I was thinking about an example, how to present it to the people of Geneva, and I realized I should do it with construction sites in the traffic. You see. So if you're driving through Geneva, there tend to be construction sites where you actually have to slow down, go to very low speed, and then you have to accelerate again, and that, of course, costs energy. And the energy costs in a wire are, in fact, quite substantial. So for the standard high power lines, high voltage lines, the utility lines, as you know, so the average household number for the energy loss is 50 watts per meter. Actually, it doesn't matter too much at which voltage such a line operates. 50 watts per meter is the loss. So one could actually illuminate a light bulb, a nice light bulb, at every meter of a high power line. This energy is lost. This is electricity which is generated, but it's lost and just used to heat up the atmosphere. It's over a length of 40 meters that so much power is lost that one could drive or supply a Swiss household with electricity. So every 40 meters, the energy of one household is lost. And this is, of course, a big waste of energy. In classical physics, there's no way around to save this energy because copper and aluminum are already excellent conductors. But quantum physics offers a way to solve this. And this is, again, a beautiful and bizarre effect. And the effect becomes obvious if one cools down such a conductor to low temperatures. And with low, I really mean low. So in your freezer, you may have minus 18 degrees centigrade. The coldest temperature ever measured on our planet is about minus 90 degrees centigrade in the Antarctica. I'd like to go lower to the temperature, which is of minus about 194 degrees centigrade, which is so low that actually the air becomes a liquid. So it's not the moisture of the air which condenses out, but the nitrogen and the oxygen of the air itself become a liquid. That's the temperature with which the liquid oxygen in the space shuttle is cooled to. And to give you a further feeling for the temperature scale, the absolute lowest temperature is absolute zero. It's at minus 273 degrees centigrade, which is about the temperature of the background temperature of the universe, which is 2 degrees above this absolute zero temperature, which is the heat left over from the Big Bang. And the effects I'd like to describe, superconductivity, happens in this temperature range between absolute zero and somewhat above the temperature where air liquefies. If we take the aluminum and cool it down to close to absolute zero, something funny happens. The electrons in this aluminum, they lose their identity. The electrons decide, all of them, to go ahead and to form, as I've drawn here, one super wave. The electrons, all electrons behave basically, essentially, like one giant wave of one electron. And this wave, usually the waves just have the size of an atom. But in this case, this giant wave extends from one end of the wire to the other end of the wire. This is a really astounding effects the electrons do here. And I'd like to say that Professor Ketterle, who'll be talking tomorrow, can do the same with atoms. He cools down his samples to much, much lower temperatures, to within millionth of a degree to absolute zero. And he manages that the atoms lose their identity and form such giant waves. It will be very interesting to listen to him tomorrow. Now, if one has such a giant electron wave, the current flow happens in a completely different way. Because you can imagine that these waves, they don't care about the defects, they don't care about the vibrations. They can transport the current without any losses. Coming back to the construction side, it's like if you look how wind passes, breezes through the construction site, it does not care, it just flows through it. So that means that the current can flow without losses. There's no resistance if the material is cooled to such low temperatures. And in fact, this sounds very academic and esoteric, but this is a very common effect, and I'd just like to illustrate it to you here. I've a little demonstration. I hope I can show it to you. So here I have such a superconductor which shows this effect. This is a cuprate, copper oxide, and this superconductor becomes superconducting if cooled down to the temperature of liquid nitrogen, of liquid air, and therefore I have here some liquid air with me. And this is the material on which Professor Fischer works, and the material, or related material, to the one which was discovered at the IBM lab in Rüschlikon by Alex Müller and by George Bednarz, for which they received the Nobel Prize. At that time, this was a very fancy discovery, and one dreamed about many applications, and it took now about 20 years, 25 years, that these applications are ready, that these wires have been fabricated and built, and I'd like to show to you what can be done with these wires. And at that point, I'd like to correct Oyston a tiny little bit. He said that the basis for these wires are the effects which I perceived of aligning the grains in these conductors. Of course, I was part of a small group working on this issue, and the idea is the effort of the group. It's my colleagues Duane Demas and Praveen Chowdhury and myself who provided the basis here. So it was not just me. So to illustrate to you how it works, well, I first have to, now it becomes complicated, I have to switch the camera here. I need to concentrate. Yeah, that was the difficult part. So what I have here is an experiment. Namely, I have here a wire, and I am sending through this wire an electric current, which is generated by this power supply. It's 3 amps of electrical current. And when flowing through this wire, energy is lost, so I measure the voltage drop along this wire, and that's done with this instrument here. And you see here the reading of this instrument. So this is you. This is the instrument. And that's the energy lost in the wire. Okay, it's a measure of the energy lost in the wire. And there's energy lost because, as you can see, the wire is lying on the table. So it's warm, it's at room temperature, it's not superconducting. The electrons are just individual electrons hanging around, every one on its atom, and they are rushing, they are bumping into the construction sites. Okay? And now I'll take this wire and cool it down. So I have liquid nitrogen, which I'd like to... my wife now gets really nervous. So you may see the liquid nitrogen now pouring down. In fact, I'll spill it a little bit that it makes a nicer fog. Okay. And now I take this wire and just dump it into the liquid nitrogen to cool it down. And please watch the losses of this wire as the current flows through it. The nitrogen will, of course, now start to bubble and boil, and it needs some time to cool down. So now it's at minus 200, minus 100. You see how the losses go down, and now this super wave starts to condense. Okay, the losses are really very, very small now. It's still boiling, it's still not really cool. You see, it will stop bubbling as it does. You see? And the losses are gone. The losses are really zero. Thank you. Now I'd like to take it out before it starts to be minus 1. And here, I mean, let me make it clear. The electrons form this gigantic wave, this super wave. And as I take it out, if I'm quick, I actually can touch this. It's cold, but I can touch the super waves with my fingers. And that's really quantum physics. As you see, as it warms up now, the losses start to become big again. And these wires are excellent conductors. So they don't only conduct electricity without any losses, but they also can conduct enormous densities of electricity. To illustrate it, this is a standard cable which we have in Augsburg in the ground, which can carry 400 amps of the utility company in Augsburg. And you'll have in Geneva the same cables which transport the power to your villages and houses and so on. And this is the superconducting cable, and it carries the same current as this cable here, as the normal cable. But you see how much smaller the cross-section is. The current density is so enormously high. And in fact, the cross-section here is just given by the steel which is needed to stabilize the cable. The superconductor is so small you cannot even see it. So, such cables are now used worldwide. That's how such a superconducting cable looks. Here's the superconductor. It's cooled with nitrogen flowing in here. And that's, for example, a cable that is put in ground in Long Island, close to New York City, where it's used on a daily basis. Also, because the superconductor is carrying so high current densities, it's a beautiful material to make magnets. And the CERN, for example, uses 27 kilometers of such magnets to hold the beam in the tunnel. Without superconductors, it would not be possible to build the LHC. The superconductors nowadays are used for topics which were unthinkable a few years ago. And one is to build very efficient heaters. To make aluminum profiles like this one here, one presses aluminum through orifices, and to do so, one needs to heat the aluminum to high temperatures, to 500 degrees, 600 degrees C. And to heat 1 ton of aluminum, one needs the power your household needs within a week. And in Europe alone, 3 million tons of aluminum are heated up every year. So that's an enormous amount of power. With standard heater, half of the power is lost. One can use now superconductors as a heater just by generating magnetic fields with a superconductor and then rotating the material in the magnetic field, as is done, for example, in this furnace. Here you see such a glowing rod of aluminum. And the superconductor cuts down the losses to a fraction, to a very small fraction. of the losses before. So here is an issue where superconductors will, this high temperature superconductors will make also a very big impact in saving energy. Magnetic resonance imaging is a technique which you certainly know, which also uses superconductors. How does MRI work? This is a very nice technique to make three-dimensional images of the inner parts of your body with a resolution of about 1 millimeter without exposing you to any radiation. It works the following way. The nuclei in the atoms in your body are small magnets. And in an MRI machine, there's a big magnet which aligns the nuclei in this outer magnetic field. Now, the different elements in your bodies are different magnets. So hydrogen, which is found in the blood, is a different, the nucleus is a different magnet than calcium nucleus found in your bones. As these magnets align in the magnetic field, they send out electromagnetic signals, electromagnetic waves, which are picked up by detectors, by antennas, which are then used to image the body. So, in these systems, there's this magnet, this is the magnet, which is cooled down close to absolute zero, 4 degrees above absolute zero. So if you're in an MRI machine, there's this liquid, in this case liquid helium, all around you, which essentially has the temperature of outer space. And in there is a current flowing in a superconductor without any losses making the magnetic field. Let me mention that the losses are so small, are zero, that the current is actually put into these magnets in the factories as the magnets are built. And then the magnet with a flowing current, it's just, there's no battery, no power supply, it's just short-circuited, is flown to the hospital, installed in the hospital, and it's the very same current that circles here that was put into the coil in the factory. So one can take really very nice images, high-resolution images, 3D images of the body with these systems. Here is another application. Because the waves are in the superconductor, because there are no losses in the superconductor and it's cooled to low temperature, the superconductor has very little electric noise, so one can build very nice detectors with the superconductor. And here's one example. This is the Herschel spacecraft. It's the telescope with the largest mirror that has been put into space. It has a diameter of 3.5 meters. It was launched last year with an Ariane rocket. It's an infrared telescope which watches the space. And here, for example, it imaged the Rosette Nebula in outer space. This nebula is 5,000 light years away. It has a, for you, if you look at it with a binocular, for example, it has a diameter from here to here of 5 radii of the moon. So the light needs 25 years to travel from here to here. And this is an interesting area because in this nebula, stars are born. So you can see here protostars, star babies, which are born. And one can watch how the synthesis of stars, how the formation of stars works. So this is a beautiful image taken with standard detectors, non-superconducting detectors. But can you see here actually what these clouds are made of? You cannot. But if you have superconducting detectors, you can do spectroscopy, and that has been done here. And one can analyze from here, from the Earth, which molecules are around in space 5,000 light years away. And one finds, for example, that there are organic molecules in the Rosette Nebula, sulfur dioxide, and also water. And this is just, again, the use of superconductivity. Another issue, another question. If you have a problem with your heart and you go to the doctor likes to do electrocardiography at your heart. So puts up this contacts onto your skin, and by doing so, he can measure, or she can measure, the electrical voltages generated by the currents flowing in the heart, and that is used to analyze your health, which is a standard and important procedure. That unfortunately does not work with unborn babies. In many cases, or there are cases where one can find, for example, just with ultrasound or by listening to it, that the heart of an unborn baby in the mother's womb has problems. But one cannot do electrocardiography because these electrical signals are perfectly shielded by the water in the mother's belly from the outside. So this is a problem because one frequently would like to know whether one needs to do an operation before the birth or one can go through the birth and so on. Superconductivity actually provides quantum physics a problem, a solution to this problem. And this is done with such a small ring as I showed in the beginning. So here's a small ring of a superconductor evaporated onto an insulator. So we have the ring which we discussed in the beginning. The current flows through here. And as you have seen, small magnetic signals, small magnetic fields penetrating the loop of the ring change the resistance of the ring. And it is such that very, very small, tiny magnetic fields influence the ring, which makes these rings the most sensitive magnetic field detectors which we know. So one can actually use these detectors, which are called superconducting quantum interference devices, SQUIDs, to image and to measure the magnetic fields generated by the currents of the baby's heart, which are not shielded by the mother's belly, as done, for example, in this machine. And here's an example. This is such a magnetic signal. So here's time, here's magnetism. This is, as you see, a 10 millionth of the strength of the Earth magnetic field. So a baby generates small magnetic fields, as you would have guessed. These are the magnetic peaks of this heartbeat of the mother. This, at a different frequency, the magnetic heartbeat, the magnetic signal of the heartbeat of the fetus. And in this case, one analyzed it. One knew that the baby had a problem. One saw by analyzing it, okay, one may actually go through the birth. One doesn't need to have an operation. The baby was born and then treated and is now healthy. And imagine, the baby profited from our knowledge and how electrons flow around these little loops. I find this completely amazing. Here is another application. Here we have the magnetic field detectors at the end here of this tail boom of this Cessna. And with this sensors, one can image, of course, and measure the magnetic field generated by mineral deposits in the ground. So these systems are used to search for mineral deposits and actually also for unexploded ammunition in war zones. And by using such detectors, such SQUIDs, built from these high-temperature superconductors that were discovered here in Zurich, one has found mines already, mineral deposits worth $5 billion, in particular nickel, silver, and also diamonds. So one detected here the kimberlite in which the diamonds were embedded. Okay, this was the second message of my talk. The quantum world is beautiful and bizarre, and now quantum physics is obviously highly useful. But you may still say, okay, I don't care, because I'm not really looking for minerals, and I'm also feeling healthy, so I can ignore it here. Which brings me to the third part of my talk. And I'd like to make clear to you that coming back to life, that life actually is based completely on quantum physical phenomena. That's the way I put it. My former colleague Don Eigler used different words. He said, "You are a bag of quanta." And I have 3 examples. Number 1 is your genetic information. Of course, your identity, you yourself, are shaped by your DNA, by your genetic code. And your DNA, the information is, of course, written in the letters of the base pairs along the DNA, so the way these bases here pair up. Of course, your body is shaped by evolution, by mutations which happened with these base pairs in reading the pairs and copying the pairs. It turns out that the mutations in the base pairs, the mutations of the DNA evolution, is influenced to a significant degree by the tunnel effect, which we discussed half an hour ago. In this case, it's not tunneling of electrons, but it's tunneling of the course of the nuclei of hydrogen atoms, of protons, between the base pairs, which give rise to mutations. So without the tunnel effect, this esoteric effect which we discussed half a year ago, we would not be sitting here. Evolution wouldn't have happened. We would be, little slimy algae swimming in the primordial soup. In fact, without the tunnel effect, also the sun would not be shining because the fusion processes are shaped by the tunneling. The stars wouldn't have worked the way we are. And the stars have, of course, synthesized the elements out of which we are built. So the carbon atoms out of which we are built are there because of the tunnel effect. Without the tunnel effect, your body parts would not be there. The genetic information also influences, of course, how the proteins in your body are synthesized, the very basis of your life. And this is done the following way. Here's I should darken it down now a little bit more. Sorry about this, but it's just 2 minutes. So the proteins are not copied directly from the DNA, but there's a second molecule, an RNA, being copied from the DNA, and this RNA is then the template for the proteins. This writing, this generation of the RNA is done in a little molecule called RNA polymerase, which in this film here is this green blob here. And this RNA polymerase, just unzips a little bit of the double helix of the DNA, takes the building blocks for the RNA, which enter this RNA polymerase, and then synthesizes the RNA here, which snakes out here from the top, which then is used to synthesize the proteins which you need for your life. So this process here, as you see here, is of course a process which is pure quantum physical. There are no wheels, no levers. And this process right now happens millions and millions of times in your body. But it even gets a little bit more frightening, because the nerve signal in your body, they also are driven by quantum physical phenomena. They, of course, pass from one nerve cell to the next nerve cell. And the nerve cells haven't merged perfectly, but they touch just each other. So how is the information being transported from one nerve cell to the other? Well, the signal travels in one nerve cell as an electrical signal down until the end of the cell, where then there is this synaptic gap to the next nerve cell. And as the electrical signal approaches the end here, it releases molecules, the green blobs here, neurotransmitters, which pass through this gap and then trigger a signal in the second nerve cell, which then continues. And of course, again, how the electrical signal passes in the nerves, how these neurotransmitters are released and pass through this gap, that's all quantum physics. This biochemistry is based on quantum physics. So the thoughts in our brain, the way we are thinking, what you're thinking right now, your self-consciousness, is all based, rooted in quantum physical phenomena, in this very weird, bizarre phenomena. Thank you very much for your attention.
Thank you very much, Jochen, for this fabulous introduction to quantum physics and its importance, and of course it's a beautiful introduction to the week, the rest of this week here. And you really met the challenge.
Thanks.
We are now coming to the second part of this manifestation here, namely the questions. And those of you who want to leave, of course you should do that, but I think there will be a number of interesting questions that will come up, so I encourage you to stay. You know the way it goes. There is a small paper on each of the desk where you are sitting. You are supposed to write your question there, and there are nice people going around picking up the question and will bring it forward to us here. Je répète peut-être en français. Donc, vous avez des papiers que vous pouvez remplir, poser des questions, et nous les distribuer ici. Et on va mettre tous les orateurs de cette semaine vont venir devant ici et répondre à vos questions.
Dankeschön. Thank you.
Excellent job. I have a few issues. We can
I
discuss
think
them
so.
later.
Ich habe darauf gewartet, dass als letztes als Titel kommt Sex und Quantenmechanik.
Das ist dem nächsten Sprecher überlassen.
A lot of people are leaving.
Wahrscheinlich gibt es einige Biophysik, die auch dabei von
Klar.
der Quantenmechanik kontrolliert wird.
Mit Sicherheit. Das ist toll, wie groß das Interesse ist.
Das ist fantastisch.
Die schweigsame Hand ist schon richtig.
Was ist genau quantenmechanisch beim Halbleiter? Die Bandstruktur?
Klar, ohne Quantenphysik wird es kein Gap geben.
Also in dem Sinne kann man vertreten, dass alle Halbleitermaterialien auf Quantenphysik beruhen.
Ja. Natürlich im Prinzip alle Materialien, weil sonst wird es ja keine Bindung geben. Ohne Spin keine Bindung.
Okay. Im weitesten Sinn, ja, man kann natürlich auch sagen, die Devices sind wirklich Quantendevices, wo noch Tunneln stattfindet.
Es gibt gibt wahrscheinlich verschiedene Tiefen von quantenphysikalischen Prozessen.
Chemie ist Quantenphysik.
Chemie ist
Bindung,
Quantenphysik.
Orbitale.
Und am anderen Ende gibt es dann natürlich Qubits und so, das ist dann der andere extreme Fall von Quantenphysik.
Gut, es gibt Physik, ich meine, deshalb haben es ja die Leute erst so spät geschnallt, dass man kann sagen, die ganze Stabilität der Materie ist Quantenphysik.
Ja.
Wenn man natürlich die Frage hat man sich halt vor 150 Jahren noch nicht gestellt, warum Materie so ist, wie sie ist.
Es wurde ja kurz vor Beginn der Quantenphysik war ja unklar, ob es überhaupt Atome gibt.
Aber es gibt eben Quanteneffekte, die praktisch die Stabilität der Materie sind, die Eigenschaften der Materie. Dann gibt es Welleneffekte wie Tunneln und dann gibt es Effekte, die nochmal...
Mit der makroskopischen Kohärenz, die nochmal quantenphysikalisch sind.
Makroskopische Kohärenz und dann gibt es natürlich wenn Entanglement und nicht Lokalität verwandt ist in verschiedenen.
Je pense qu'on arrive lentement au début des questions. On a déjà une collection ici. I will switch to English so that our guest will follow more easily. We have a first question here, which is, why is the decrease in resistivity not brutal but rather progressive? Superwave mode is a brutal change or not? Jochen, that's to you.
So if one cools a superconductor and in changing the temperature, the resistance actually jumps from a finite value, from a significantly large value to zero. It's just the way I performed this experiment which didn't show this effect. There were other effects hiding it up. For one thing, to be sure that the experiments worked, I had switched on a large filter in the electronics in the voltmeter, which made the reply of the voltmeter relatively slowly, so the jump was smeared out. As a second thing, this wire, which I cooled down, was very long, 20 centimeters. So it didn't have the same temperature at all the positions, but it started to become superconducting at the central part, which was cooled best. So this part switched to the superconducting state, but it was a little part, so the resistance only went down a little bit. And then more and more of the wire became superconducting, and as it cooled down along its length, the resistance disappeared. So these are just artifacts on the way I did the experiment. In principle, physics-wise, the resistance shows a jump as a function of temperature.
Thank you. Here is a very different question. In the very cold outer space, why can't we transport radiant electricity since resistance is down to almost zero? So maybe one of the other speakers would be interested in that question. So why can't we transport resistivity in outer space? Yes, Professor Gross.
Well, in a sense we do. They're cosmic ray protons that come unimpeded over most of the galaxy. But the interstellar medium is pretty dilute and empty and doesn't have charge carriers like an ordinary metal to carry an electrical current.
Okay. Somebody wants to add something to that? I think this is... Yes?
Well, maybe let me add that the major limitation why we don't find superconducting cables all over the world is the requirement of cooling them to low temperature. This refrigeration, the cryogenic infrastructure is in many cases prohibitively expensive and complicated, but this problem would not exist in outer space. Outer space is cold enough that many of the materials we know right now would be superconducting. So therefore, if we want to have transmission of energy in outer space, a superconductor would do that, but of course we have to transport the superconductors and bring them into outer space.
Thank you. Jochen, you want to...
May I add? So it's possible, and I think it is done, that when I uses the temperature of satellites, just circling around the Earth, for example, to cool superconductors to temperatures that they are superconducting, and use superconducting effects, just using the low temperature of space. So in some satellites, I think this is already done.
I think that your explanation or your example of yourself tunneling through the wall over there maybe has created a few questions in the audience. And here is a question. I myself, am I, ball or wave? Since I'm not able to go through the wall, I'm more ball than wave. So
You're more?
more ball than wave. I mean, you have a particle and you have a wave, so he thinks, the question is, the person thinks that he is more particle than wave. So how can we answer that question? Yes, Alan Aspe.
Well, in a sense, you are a wave, but you are a wave which extends over such... Ouais, je peux répondre en français, non, à Genève, n'est-ce pas? Bon. Donc, dans un sens, vous êtes une onde, mais cette onde va s'étendre sur une distance si courte qu'il faudrait un mur tellement fin pour que vous puissiez le traverser que c'est assez improbable. Peut-être à Genève, les joailliers qui battent l'or en feuilles extraordinairement fines, mais je crois que la réponse est oui, vous êtes une onde, mais comme votre masse est très élevée, il faut vous imaginer cette onde s'étendant à une distance extraordinairement courte.
Okay, thank you. Well, I think I don't hear protests. Is there a relation between the ways electrons behave in superconductors and lasers? So maybe here we have several experts on these questions here. So I don't know who wants to. Professor Ketterle, you want to say something?
I will say much more in my talk tomorrow, but as a little preview, yes, the behavior of electrons in superconductors has a lot in common with laser beams. In some sense, you can say that electrons, when they are superconducting, have actually or share a property with laser light.
Okay. Thank you. I have here a different questions. In l'énergie, I will say this in French, l'énergie utilisée pour refroidir l'oxygène est-elle égale à celle qu'on économise en courant électrique? So question is the energy used to cool down oxygen, is it equal to the one that we gain by the electric current? So Jochen, I think this is your question.
So this depends on the amount of electricity transported in a cable, because to cool down a cable one needs a certain amount of energy independent on how much current is flowing through the cable. The losses in the cable due to the current flow, on the other hand, increase very much with the increasing amount of current that is flowing. And it turns out that for standard cables that, for example, would supply a town or a city with power, the losses due to the cooling, or the power needed to cool, would be smaller, say a factor of 2 smaller than the energy saved. So it means a cable right now, for example, if it loses 5% of its energy due to heating, would then effectively lose only 2.5% of its energy. So one could save about half of the energy that is lost today by going to superconductors on average.
Thank you. What about quantum physics in the field of acoustics, particularly in bioacoustics and psychoacoustics? Somebody wants to say something about acoustics. Doesn't inspire. Yeah.
Well, I'm not an expert on acoustics, but my understanding as a physicist is that acoustics is, most of it is classical effects. So when we communicate, when we talk to each other, the sound waves can be described classically. Of course, when you say acoustics is the motion of pressure waves, it's the motion of air molecules which eventually transmits the sound. If you go to the nano world and ask what is acoustic, what is the equivalent of acoustics in the nano world, we go down to some vibrations of only a few atoms, and that again is quantum mechanics. But acoustics as we understand it in the common use of the word is purely classical.
Thank you. Somebody wants to add to that? No? There is a question here about... Sorry? You just agree, yeah. That's reassuring, I think. The tunnel effect seemed to be a bit mysterious. Could you explain more in detail the tunnel effect? Why is it the basis of so many applications? Or is there a way to explain that? Yeah, Professor Blatt.
I may add something to the tunnel effect. Very many people wonder whether that's really something purely quantum. The tunnel effect is actually an optical phenomena that we all know. It's not very often used, but it's known. It's actually a wave phenomenon, and whenever you then have to resort to a wave description, as we have learned in quantum physics, then of course the tunnel effect comes about. So what's the origin of this tunnel phenomenon if you have waves? For example, take a window pane, and you have, for instance, light transmitting through that pane. Then of course you also find, when you look at a very shallow angle, that there is a total reflection of the light that we all know. But that total reflection comes also with some leaking electric field on the side where you shouldn't have any light. And this can be used when you become very close to that surface, for instance with another surface, another prism or with a window, that some light can be coupled out. So we know this wave phenomenon. This can be used with microwaves, it can be used with any kind of wave. And as soon as we now describe matter and the quantum world with waves, then this phenomenon is clearly there too. This is what we call the tunnel phenomenon. And since you can use it in such a wide variety of things by coupling a wave over a gap, then of course you can use it in transistors and all of other applications that makes it so useful.
Okay, thank you. Yes, Alan Aspect.
Yes, I would like to add a comment. Of course, what Rainer said is totally true, that the tunneling effect is first an effect of wave. So after all, I have a wave coming on an interface, should not get through, but a little wave leaks out of it. We can understand it. But if now, rather than having light, we think of matter, we think of an electron, and the small wave of this electron arriving in a similar situation. But at the end, sometime you find the electron, which is a particle of matter, on the other side. So I think that this allows us to emphasize the weird, the bizarre character of quantum physics. The bizarre character of quantum physics is evidenced when you have a wave behavior that you apply to a particle. Because when it is a matter particle, which at the end is on the other side of the wall, it's more bizarre than when it is only a wave.
Well, yes, Professor Gross.
Quantum mechanics is very bizarre, but I would like to emphasize a slightly different way of looking at this, which is where we've gotten to in physics today. The world is quantum mechanics. It's not just that some phenomena in the world are quantum mechanics. The whole world is quantum mechanics. The interesting goal sometimes is to try to explain the world that we're accustomed to from quantum mechanics. You run into paradoxes and trouble when you try to do the opposite, which has been well illustrated here in the lecture today. When you try to explain or illustrate the quantum world that we understand quite well, described by the Dirac equation and other quantum equations, when we try to explain that quantum world or visualize it in classical terms, then you run into all of these seemingly paradoxes, bizarre features, and they're correct, but they're sort of an approximate classical way of trying to describe reality, which is quantum mechanics. The waves are a way of describing the behavior of dynamical variables or particles or whatever we believe are the elements of our description of the quantum world, but they're not waves in space. So one problem with visualizing, just giving a wave description of the quantum world is that these waves are not waves in three-dimensional space. They're waves in another space, which hasn't yet been talked about here, called Hilbert space. And therefore, certain phenomena which can be easily described in classical terms, in terms of waves, such as certain aspects of tunneling or certain tunneling effects, don't work in all cases. To really understand them, one has to develop a quantum way of thinking. Now, that requires much more than 5 talks, and is why we're forced to give classical pictures which seem very bizarre. And there's nothing we can really do about them, and inevitably there will be a certain lack of concordance between these classical illustrations and pictures and the quantum world.
I have here a question that maybe would be interesting to answer. Dans quelle mesure l'information, nos pensées, croyances, influencent la matière? Hypothèse, si je crois très fort que je peux traverser le mur, cela pourrait-il augmenter la probabilité que cela soit possible? So
if I believe strongly that I am going to cross the wall,
I will translate this in English. To which extent does the information, our thinking, or our beliefs influence the matter? The hypothesis, if I believe very strongly that I can get through on the other side of the wall, does it increase the probability that this is possible? So,
try harder.
if you believe it, you will try harder. I wonder whether one of you want to say something to that question.
Well,
Don't try it.
determination always helps. If you're determined to do something, it helps you to achieve it, but it's not a guarantee. And I'm afraid in that case, it won't help you. You can't really beat the odds of physics. And what happens is the wave character or the tunneling happens on a scale which is given by the quantum mechanical wavelengths or the de Broglie wavelengths of the object. And once it comes to the size of a human being, the de Broglie wavelengths is shorter than the size of an atom or the size of a nucleus. So therefore, the tunneling phenomenon is limited to distances which are much shorter than much smaller than your body itself. It's not a contradiction. You can talk about the wave which describes the center of mass motion of your body. But the center of mass motion of your body corresponds to the Broglie waves, which have a wavelength shorter than a nuclear diameter. So therefore, I wouldn't even try it. I wouldn't even run against the wall.
Les ondes qui sont constituées dans la matière sont-elles formées seulement par les électrons et les photons, ou bien d'autres particules différentes forment elles aussi les ondes? This is a more practical question in a certain sense, and I think there are many answers to that. Who wants to say something to that question?
I think the answer is yes. I mean, the question is, do we have wave for every particle? The answer is yes. Oui, en physique quantique, toute particule est décrite par une onde de matière, que ce soit un électron, un proton, n'importe quelle autre particule. Not much to add. Si, David?
Well, waves of what? So in our present theoretical understanding, we have the waves are waves of fields, like the electromagnetic field, and light is a wave of the electromagnetic field. You might ask, is that field correspond to the vibrations of some medium? We learned from Einstein and Maxwell originally that no, this is just a field that exists in space. We associate every particle, every elementary particle, with a field. And the vibrations of that field, the quanta of that field, are both wave-like and particle-like. Much as the vibrations of the electromagnetic field are wave-like, but they come in quantized units, electromagnetic quanta, photons. That might not be the ultimate description of nature. We now play around with an idea called string theory, which I'll discuss a bit, in which that's only an approximation to the way we describe the elementary constituents of matter and radiation. But the waves are waves of fields, much like electric and magnetic fields, except there are other fields, the electron field, the quark fields. And those are, the quanta of those fields are all the elementary particles of radiation, of force, and of matter.
Thank you. Non-locality is one of the bases of quantum mechanics. How about the time? Is the wave function also correlated in time? So, is the wave function also correlated in time? That's the question. La question, est-ce que c'est corrélé dans le temps?
If by correlation in time you mean that an event that takes place here and now will affect you slightly afterwards, yes. That's the nature of physical reality. Events influence events that occur in the future. So the description of physical reality, of course, contains within it causation. And the business of physics, in large, is describing that causal relation between the past, the present, and the future. If by what you mean that an event that occurs here and now can influence another event at the same time, somewhere displaced in space, so that a signal of light, which is the fastest propagation we know of, cannot propagate from this event to that event, no. Not even in quantum mechanics. There is no non-local causal relation between different parts of the universe due to quantum mechanics. That would violate our understanding of causality.
Thank you very much. Jochen, you want to add?
Yeah, I'd like to add that there's a little twist to it. The active word there is causality, and any mechanism with which information can be transported from A to B just can be done with a maximum speed of light. Yet in quantum physics it is also such that one can actually have two wave functions in two different places, and it's important what happens to a wave function at place A to what is happening to the wave function at place B. So if a wave collapses, for example, at a certain position, a wave at another place at the very same instant changes. This effect cannot be used to transport information, so it doesn't violate special relativity or whatever. But this effect is there, and it has been demonstrated here.
I see some reactions.
If the audience pushes this panel to discuss interpretational issues of quantum mechanics, our unanimity will disappear.
Yes.
In fact, it already has disappeared.
So,
so I slightly disagree with Joachim's description of what we both agree are the results of experiments that can be can be predicted from quantum mechanics and have always been verified. But this debate might be interesting to watch, but I'm not sure we would come to a conclusion. The kind of non-locality that he's talking about is one of interpretation, I would say. The fact that one cannot transmit information over regions which, by our understanding of relativity, are acausally disconnected, is, we both agree, a fact. And how we interpret that in terms of our interpretation of quantum mechanics, trying to avoid the word collapse, for example, is a matter of an area of physics which somehow doesn't affect either our predictions or our measurements.
Jochen,
Yeah,
you want
well,
to?
yes.
Okay.
Well, I would like first to advertise the talk of Thursday, where this question will be addressed, and one point on which I think we are going to agree is that this question of non-locality happens, as you said, when we try to find images in our three-dimensional space, a space where we live, for phenomenon on which we agree when we describe them in an abstract Hilbert space. All the difficulty is there. When we try to describe it in that space, then things like non-locality appear in the images that we develop, but we all agree on the fact that we cannot use this non-locality to transmit useful information faster than light, or whatever useful faster than light. But personally, I like to have non-locality in the images that I develop in this world. For me, it's useful, but we all agree at the end on the result of the calculations.
I would urge my colleagues and all of you eventually to learn to live in the quantum world.
And that's what it is all about this week. I think we are getting close to the end of this session of questions. Maybe I'll ask one more question, which is of a more practical nature, to Jochen Mannhardt. Les supraconducteurs peuvent-ils être utilisés pour transporter l'électricité sur des grandes distances? Où en sont les recherches et expériences allemandes à ce sujet? So I will say it in English. Can the superconductors be used to transport electricity on long distances? And where are the research in Germany, for instance, suppose in your case, on this topic? So what can you say about that?
Yes, superconductors can be used, of course, to transport power, in particular large amounts of power along long distances. Right now, the status of the field is such that about a dozen of superconducting cables are with high temperature superconductors are being operated in the world, and more are coming. Actually, as far as basic science is concerned, as far as research is concerned, the research to a great extent has already been done with this copper-rate superconductor. So right now it's just a matter of engineering and getting costs down, which is done at many places in the world. I have to admit that the research efforts and this development efforts in Germany are actually relatively small, which is very disappointing, because these cables are a nice, efficient way to transport power, and a developed high-tech country like Germany, which is using a lot of electricity, I think, needs to be able and capable to produce and use the best cables possible. So a lot of research is done in the US, where there was a very strong effort, which involved, for example, the national labs like Los Alamos and Oak Ridge and companies like American Superconductors. There's a lot of research in Japan and also in Asia. Not so much at present in Germany, I'm afraid.
Thank you. I guess this is coming slowly to an end. I would like to thank, first of all, Jochen Mannhardt for his talk. Then those of you who are accustomed to the Wright Colloque has noticed that we have all the 5 speakers of the week here today, which is extremely nice, and I would like to thank all of you for your contribution and discussion. And then we have a rendezvous demain à 18h30 pour la conférence du professeur Ketterle. À demain. Merci.